Hi, I'm Dan LaChapelle, PhD candidate in aerospace engineering at the University of Texas at Austin. I'll be presenting a method for automotive collision risk estimation under a cooperative sensing paradigm. We're excited to share this research with you. On the next slide, you'll see a short video that highlights the crux of the problem we're trying to solve. The traffic light will shortly be green. The vehicle whose point of view we are seeing, which we term the ego vehicle, has every right to proceed through the seemingly clear intersection. However, a pedestrian, our very own Dr. Todd Humphreys, emerges from behind a bus just as the ego vehicle is about to accelerate. Disaster is narrowly avoided. Automated vehicles will need to be able to handle situations like these, where some road users might be breaking the rules. But also, Dr. Humphreys should learn to look both ways before crossing the street. We at the University of Texas Radio Navigation Lab predict that autonomous vehicles must be between 2 and 100 times more reliable than humans, based on the measure of roughly 100 million miles between human-caused automobile fatalities. Towards solving this problem, we frame our work in terms of a trilemma, a choice between 3 undesirable options. Automated vehicles, when they lack enough information about their surroundings to make critical decisions, face a choice between crashing, crawling, and cooperating. They may crash if they lack information about nearby hazards, and they are unaware of that shortcoming. Alternatively, they will slow to a crawl if they know that they lack that information for safe decision-making. On the other hand, they may seek to remedy the situation by cooperating with nearby sensor-equipped vehicles and sensing infrastructure. Cooperative sensing, while clearly the path to safe autonomy, comes with issues of its own. Data exchange may be limited by bandwidth and cost considerations. There's also the challenge of ensuring that data from external sources is trustworthy enough to base safety-critical decisions on. Finally, data about one's surroundings requires both the source and the recipient of shared sensing data to know each one's pose within a common reference frame. The main contribution of this work is to present a framework for quantifying the benefits of cooperative sensing and to demonstrate its use. The technical approach can be broken down into 3 parts. First, we estimate precise poses for the vehicles. Second, we combine sensor measurements in the form of ranges to obstacles into a shared probabilistic dynamic occupancy map. Third, we use the vehicle poses in the occupancy map augmented with a cost function to compute the expected cost, or Bayes risk, of collision. The risk measure is accumulated over all cells where our ego vehicle may exist, according to its pose uncertainty, and added for each time step to produce an estimate of accumulated risk at each epoch. A necessary condition for useful cooperative sensing is precise localization. By precise, we generally mean that position data must have errors of a few centimeters or less. While this is a high bar to clear, it is eminently within the capabilities of vehicles equipped with commercial-grade GNSS receivers and antennas. Additionally, we wish to demonstrate collision risk quantification with ubiquitous, low-cost sensing modalities like visual light stereo cameras over more expensive ones. Random finite set, or Rfs theory, provides a mathematical framework for reasoning about tracking multiple dynamic targets. Finite volumes of space in a grid discretization can be modeled as Bernoulli random finite sets. Grid cells are a useful abstraction for reasoning about spatial occupancy of obstacles. Dynamic occupancy probabilities are propagated from epoch to epoch with the nearly constant velocity particle model. Although it can be computationally expensive to track dynamic particles representing occupancy in unobserved regions of the map, the hybrid particle grid formulation augmented with random finite set theory enables us to explicitly handle both seen and unseen obstacles, updating based on measurements where appropriate. Representing occupancy probabilities as beta random variables when performing Bayesian updates ensures that sensor measurement uncertainties are accounted for when updating the map. The hardware we use for data capture to demonstrate our approach is the University of Texas Sensorium automotive sensor platform. The Sensorium is equipped for dual antenna triple frequency GPS positioning alongside stereo camera and radar measurements. Of course, to demonstrate cooperation between vehicular sensor platforms, you need more than one. Both were deployed in downtown Austin, Texas, at a busy urban intersection. Here, an overhead view from Google Maps is overlaid with the centimeter-accurate vehicle trajectories. In this blind spot scenario, a pedestrian in yellow crosses the street, but a bus conceals them from the view of the ego vehicle, the blue trajectory. The cooperative vehicle, the red trajectory, provides information about the pedestrian and other vehicle traffic. Does this look familiar? You'll recognize the image on the upper right as a frame from the video you saw earlier on. Behind the pedestrian, you may have noticed the second sensorium-equipped vehicle. This animation shows the evolution of the dynamic occupancy map over time. The ego and cooperative vehicle positions are shown as black rectangles. Dark blue coloring corresponds to low probability of occupancy, while yellow corresponds to high probability of occupancy. The axes are east-north 2D position and meters relative to a known reference. Initially, only the sensor measurements from the cooperative vehicle are present. The ego vehicle's sensor measurements are included once it begins to traverse the intersection. Clearly visible are static obstacles like buildings and trees, as well as dynamic obstacles like cars and pedestrians. Let's compare the map evolution with and without cooperative sensing using two frames representing the same instant in time. In the figure on the left-hand side, the ego vehicle relies entirely on its own sensing to build the map. In the figure on the right-hand side, the map is constructed using data from both vehicles. The ego vehicle is able to use the prior occupancy probabilities established by the cooperative vehicle to improve its knowledge of its surroundings, as shown by the greater area in dark blue. Here we have the estimated expected cost, or risk curves, for the ego vehicle as it traverses the intersection as a function of time. The initial increase is due to the ego vehicle's proximity to the other road users and the blind spot introduced by the bus. The plateau occurs where the sensing is sufficient to clear out the intersection. That is, the intersection is known to be more or less empty, so little additional risk is accumulated. Lastly, an increase occurs where the vehicle exits the dynamic map and enters the unknown. Estimated 1 sigma values are displayed with dashed lines. Not only does cooperative sensing reduce the estimated collision risk, it increases our confidence in our risk estimate. Back to the trilemma, a choice between 3 undesirable options. Automated vehicles, when they lack enough information about their surroundings to make critical decisions, face a choice between crashing, crawling, and cooperating. In this case, the ego vehicle's driver elected to initially crawl to avoid colliding with the pedestrian. But we can see from the plots on the last slide how cooperation would have helped as well. Of course, our scenario was conducted in a way that ensured a safe outcome. However, that may not always be possible in real life. The ultimate goal of this work is to permit automated vehicles to achieve high safety standards without sacrificing performance. We are still working on how to best conduct the cooperation we presented, but we believe that this work quantifies the need for it. Thank you for attending my talk, and I hope you all stay safe and healthy. Thanks also to Honda Research and Development Americas for funding this work, and to Dr. Humphreys and the rest of the Radio Navigation Lab for their support. I welcome your questions. If you're not watching live, I encourage you to email me. Back to the trilemma. A choice between 3 undesirable options. Automated vehicles, when they lack enough information about the surroundings to make critical decisions, face a choice between crashing, crawling, and cooperating. In this case, the ego vehicle's driver elected to initially crawl to avoid colliding with a pedestrian. Of course, our scenario was conducted in a way that ensured a safe outcome. However, that may not always be possible in real life. The ultimate goal of this work is to permit automated vehicles to achieve high safety standards without sacrificing performance. We are still working on how to best conduct the cooperation we presented, but we believe that this work quantifies the need for it. Thank you for attending my talk. I hope you all stay safe and healthy. Thanks also to Honda Research and Development Americas for funding this work, and to Dr. Todd Humphreys and the rest of the Radio Navigation Lab for their support. I welcome your questions. If you're not watching live, I encourage you to email me.